Hello, my name is Ivan Meller. I am a third year aerospace engineering student studying at the University of Birmingham. I've been working with Xenotech at the moment doing a summer placement, and this is my presentation on wall modelled LES or flow over a high rise building using HiPer. Hope you enjoy. This case looks at an experimental setup by Polytechnic Milan, where they set up a generic high rise building model with turbulence generators, spires and bricks you can see in the image there to replicate a suburban atmospheric boundary layer. The experiment found that the building surface exhibited localized suction peaks near its leeward top corner. These suction peaks were unexpected and they are important for engineers when looking at loads across building faces. And I've been working on investigating if HiPer, Xenotech's new fast and efficient solver, can pick up these microburst events. So here you can see my mesh setup, which is the exact same working section of the experiment. It's just a little bit longer, so it gets a higher accuracy and more detail in the wake over the building. And you can see these spires and bricks which have been reproduced from the experiment, from that image, which are 2.5 meters tall, 9 across the cross section, and sizing the bricks 60 by 100 by 200, which is the same as the experiment, to cover the floor, and this mimics the atmospheric boundary layer. So the flow conditions, the experimental velocity was about 10 meters per second, but for the simulation I set it to be 60 meters per second. This is just adjusted for more efficient time stepping, and the viscosity was adjusted to keep the Reynolds consistent with the experimental value of 6.8 times 10 to the 5. The flow conditions, the angle of attack was set at 10 degrees, so you can see this set up in the top right with the wind coming up from the bottom left, which is coming from the spires where all the turbulence is. And the boundary conditions I set were far field at inlet and outlet with slip walls and an immersed wall function for the building and the spires and bricks. So the free stream turbulence. These bricks and spires were generated using ChatGPT and Claude, which were estimated from this wind tunnel photograph along with some details provided from the thesis from Politecnico Milan. What they did in the experiment to test the free stream turbulence generation was they removed the building and they set a probe in the location where the building would sit. Then they set the wind tunnel to go and measured the inflow profile. So I did exactly that with my simulation. I took out the building and I set a rake point across where the building would sit. And this took data to plot the mean speed profile, turbulence intensity, and the integral length scale. And you can see in this plot that the free stream turbulence is predicted accurately. Here's a nice Q criterion video showing all of the turbulence structures developing from the bricks and spires. You can see it generating a nice turbulent boundary layer. HiPer is a 3D compressible Navier-Stokes wall modelled LES, so it just models the flow near the wall instead of fully resolving it. It uses immersed boundary geometry representation, so there's none of the manual body fitting to the mesh. It uses a low dissipation, high order finite difference spatial scheme with third order explicit strong stability preserving marching scheme. And it has multi GPU support with nickel, which has got excellent weak and strong scaling. HiPer is written specifically for GPU hardware. For my simulation setup, I used two RTX 5090 GPUs, which has a total of 64 gigabytes of available memory. My simulation only used 30 gigabytes, so I could have got away with just using one, but that's just what computer I had set up at the time. So this led to a compute cost of 1.2 GPU hours per convective time unit, which for those who don't know is the normalized measure of simulation flow time, which kind of means the time taken for oncoming wind to travel across one reference length of the building at the free stream wind speed. The mesh got to 500 million cells, which is the immersed boundary mesh for the wall modelled LAS. The turbulence modelling was a Bremen subgrid scale model with a fourth order central finite difference, third order strong stability preserving Runge cutter solver. The turbulence generation was physical, actual spires and bricks modelled in the tunnel. So there was no synthetic turbulence used. Which leads me on to the results. So here you can see the two velocity magnitude plots. You can see the wake shown really nicely, and you can see all of the turbulence coming from the spires and the bricks and how it's interacting with the building there. Here you can see the Q criterion video of the building, so you can see all the flows coming off that, and just about now you can see all of these turbulent structures arriving from the spires and the bricks. You can see all of those. So now you're asking, how did we measure these microbursts? We set up these wake points. So I set a tile on tile A, which is on the rear leeward face of the building, which you can see in the picture here, with the oncoming inflow at 10 degrees angle of attack. And the mapping of the wake points was matching the picture in the bottom left, where you can see each individual wake point used in both the experiment and in my simulation. So the results, here you can see the two pressure coefficients against time plots. In the top right is the experimental polymer thesis, which shows CPs around -8, and the bottom left is the top 5 most negative pressure coefficient probes from the simulation, which has got a peak of around -6.5, and this peak here corresponds to the actual microburst on the right hand side, which shows the contour map of the actual tile. So the view seen there is the whole tile that was on the leeward rear face of the building. So you can see HiPer is definitely picking up these microbursts. So the question is, how often are these microbursts actually occurring? So there's two plots of the probe plate, so each square corresponds to one of the wake points in the experiment, and the graph shows how many time steps after the flow has settled, so after the first 5 time steps, and it shows how often each point has seen each set of CP values. So on the left you can see it's pretty frequent getting CP of -3, it happens quite a lot, whereas the -5 is only a couple of events where each location has actually seen these microbursts. So, what can we take from this? Cost-wise, I did this on 2 off-the-shelf desktop GPUs, which gave me 1.2 GPU hours per convective time unit. This meant that simulations with 500 million cells on HiPer without the video outputs can be ran overnight. This is done with meshes generated on ZM Cubed, which can take just from a few minutes, because it is these STL-based immersed boundary meshing versus the manual body fitting meshing. And despite the fact that HiPer is wall modelled LES as opposed to wall resolved LES, it's still picking up these highly negative microbursts. The last thing to note is I have carried out this case, so I am an undergraduate engineer with very limited CFD experience. I've never used Linux before. Admittedly, I have used a Claude license for things like syntax and generating these STL files from the thesis, so the bricks and the spires. This all shows how HiPer is easy to use, fast and efficient to run large problems like this, and shows great results. Thanks for listening.